Thanks a lot, Flip. I guess let's move on in the interest of time for the next talks. Next, we have Stefan Haag. Stefan, yeah, he's here. So I'll briefly introduce him. All right, so Stefan is a PhD student at Mercedes-Benz AG in Sindelfingen, Germany, and the University of Bonn since 2017. He was working at the radar perception team and the sensor data team at Mercedes-Benz, and his research lies in low-level sensor data fusion for autonomous driving applications for dynamic and static targets. With that, I would like to welcome Stefan, and you can take over.
Yeah, thank you very much. But can I share my screen? Yes, hello everyone. Thank you very much for the nice introduction. The topic of my talk today is co-development of automatic annotation for machine learning and sensor fusion improvement system. And if you're interested in further reading, I just wanted to tell you that this talk is based on my previous presentation, previous works from 2018 and 2019, and last year's 2020 radar conference. And to give you a short introduction, we can either work with model-based approaches in sensor data fusion or data-driven approaches. And data-driven approaches have become more present in the recent years because they perform better in many cases, especially with camera applications. Their architecture is more flexible because we can change a little bit and then just do the training again, which is easier than changing the whole fusion framework when you have traditional applications. And furthermore, you have the evaluation in them inherently because you need somehow a function that weights each. You have the loss function that gives you an evaluation, and you can compare it when you have the ground truth. But on the other hand, you really need large data sets, which can be very costly. And you're less flexible in the sensor setups. And I think this holds especially for radar. If you change a little bit, you're not aware what happens then. Maybe just a little change in the signal processing can reduce your performance. And for us in the application, we have the problems that the certification is still unclear for some deep learning methods. So our approach is to use the best of both worlds, which means we use the data-driven approaches for subtasks where they outperform the traditional approaches. And I mean, especially detection, classification, they perform better, but we want to use these results in our model-driven world. So we still need a fast collection of label data sets. And to evaluate each step, we need the object information, the trajectories, and also the annotation information, if possible, not just some box or object information. And if we have the label data, we will show that we can improve both approaches, data and model-driven approaches. So right now, we don't have that many data sets for fused data. Happily, in the last years, new data sets came out, especially in 2019, the new scenes and the Weimar data set with some hours. But the problem for them is that the radar is not the direct detections where we want to operate with our models. Luckily, the radar scenes came out this year, which gives the pure detections where you can exploit the tracking methods in the best way. But in my opinion, there's still a lack of radar data sets to evaluate the whole fusion system. And I guess this is because the radar labeling task is very, very challenging. So we had the idea to create a Bayesian-assisted annotation system to simplify the labeling task, especially for radar data. Because when you look at the labeling of these data sets, Weimar and new scenes provides boxes, but this is not possible for radar, or not that trivial for radar, where that direct detection to cluster information is given. So the labeling task is much more complex for radar labeling. We have to assign measurements, or you can call them detections, here with dynamic objects, or if you want to estimate the static world, then with static objects. This means you have select manually the clusters in a single sensor scan. I think for radar scans, this was performed by with polygons, providing the area where the object is covered. And then we want to link the clusters over time that we can get the object information. And finally, for classification, class labels have to be selected. This has many disadvantages in case that is very, very costly, because it can be performed only scan-wise. And for example, when you do box labeling, you can just label certain frames and then interpolate this over time. And the object information is not directly gained. Here with only radar labeling. It can be gained over time with tracking. And finally, hard decisions have to be made, which are not always possible with radar data when it's somehow noisy. So we defined the requirements for our Bayesian annotation system. And we said that it should allow manual supervision for serious application. I think at the end we want automation, but we need still to be sure that it's correctly labeled. And second, we wanted the automated evaluation so that we cannot just see if our labeling system works at the end, but we can also perform evaluation of our individual steps. And this allows us an ongoing parameter optimization for our tracking frameworks. And thereby it should reduce the manual effort. And this really, as far as possible, unfortunately not completely. And the idea was to exploit our Bayesian extended object tracking method for this. What you can see now that we have a paradigm shift. This means we first generate objects where we provide very precise information. And then we assign the measurements to these tracks and so get the labeling. And at the end, we have object information and measurement to track or measurement to object information from our labeling data. This brings us to the architecture of BAAS. It might look a bit complicated, but it's not that complicated when you structure it a little bit. As mentioned before, I want first gain my ground truth objects. This is our first module. And if these ground truth objects are present, we can operate on the detection level to gain the final label annotation. But we need the evaluation, and this also model-wise. So we end up with 4 modules. The input is right now only radar detections, but it can be performed with additional sensor data to get better tracking results. In yellow, you see manual steps. We perform tracking automatically. This is labeled in blue. Then we can have the correction, and then we calculate the final states. And this means not just tracking, also smoothing and some other corrections. If these ground truth objects are present, we can have the final label annotation, which is also automated. The automated feedback uses at first manual label datasets. But at the end, when we perform better, we can augment our dataset to gain also auto-label detections to improve our system step by step. So just for your for better explanation, I go show you the individual steps, because I think it's not that clear. We said we wanted to include our extended object tracking, but we have to perform it differently than in the normal case. We have to at first cover all hypotheses that are present. So this is, we have a much higher effort. But then we have our manual selection that deletes all the, for example, false positives that are a major problem with radar tracking. And we can also correct other occurring objects like track split, merge, stuff like that, so that we have really high confident tracks and with a very high accuracy. And this is especially gained with an extra smoothing step, which I will show you later in detail. A benefit of this performance is that we have not just the object state, but also the insecurities and covariances. So let me show you a small example for low confidence extended object tracking. We really track all the objects that are present. So you see it's maybe easier to track the cars, but we also want to gain the pedestrians, the cyclists, everything that is present. So we just create a high amount of tracks. And yeah, here you can see, for example, a problem with split that we can correct in the next step. And right now we are really aware that we have a number that is much too high in cases of false positives, but we will correct that in the next steps. So right now I want to show you an example how we correct it. I've already selected a single track for you and show you the performance. This is a very challenging scenario because a left turn is performed. Right now we have a split. And we can say we merge these tracks. This is performed on the detection level. This means that the previously associated measurements are now merged and a new track is calculated. Thereby we can also merge even a higher number of tracks. So now we have this bigger track that covers now nearly the whole object. But which is what is a little bit challenging is the turn. This is not detected correctly. So now when we have the smooth trajectories, we can perform the evaluation. Therefore, we tracked on the radar scenes label data set, tracked, smoothed, and tracked again the objects to get very realistic trajectories and estimators, and calculate our KPIs for the tracking evaluation. After this, we can, or we recalculate the assignment of measurement to track. We choose an approach similar to the adaptive clustering, where we chosen a core region of our object, and then for critical points, we chosen a border region. An advantage of this approach is that we can estimate our border region based on our statistic evaluation that is allowed with BAAS. So we can also improve the final measurement to track association problem, which is not just here given, but it's always present when you want to perform extended object tracking. So we saw that the border function is really non-trivial there. It has many impact factors, for example, the ego motion, reflecting objects in the area. So we can really learn here a better function for much better performance. And so this is the final association. We have fixed sizes, we have the turn detected, and so the association is now really much more accurate. So, and finally, we have to evaluate these results as well. And therefore, I've chosen precision recall calculated on detection level, and then we can calculate the F1 score and provide statistical information how our data association performs. So this is an example for a short sequence. I think it was 5 minutes. First, we have to make sure that we have covered all the objects. And yeah, this is the case. When we look at the operating steps, I showed here the individual smoothing and selection steps also. So this is not just 2, these are 5 steps. And the prerequisite that we can look on the precision is first we have to get the object accuracy right. And this is the case for object tracking. And then we see that the precision is getting better after each step. So if this is the case, we can also look at the object to measurement performance. And here we see that each step helps us to reduce the number of false positives, which was at the beginning chosen to be very high. But the problem is in our steps, it's very easy to reduce the number of false positives, but we have to keep the number of false negatives also low. So we see that this challenging task is getting improved in each step, and we have a good basis to initialize our annotation system. So what I want to talk about now is how can this help us? When you're present in machine learning, you know more data is good data. So this method allows us to upscale data sets, and we hope it can thereby improve performance. But we also can just record certain scenarios and label them very quickly. Or if you want to change your sensor setup, you can collect new data very quickly and thereby apply your machine learning system that performs maybe very good on another data set and integrate it in the new system. Furthermore, we provide already the KPIs. Here we've shown MOTA and multi-object tracking precision for object evaluation and the F1 score for the association. So you also get information how maybe your regular tracking and fusion system is working. And it is very easy to integrate further KPIs if you want to evaluate detection, classification, clustering, or trajectory estimation, whatever you want to learn. But for our approach, we go a different way. We just don't want just to improve machine learning approaches. We can also improve our tracking system, and this is an ongoing system. That means when we collect new data, this allows us to improve step by step our tracking system. So, but what we need at the beginning is a labeled radar data set. And I mean a manually labeled radar data set. But this allows us to gain even more labeled data with our BAAS system, and thereby we can also improve our tracking methods, because the tracking is inherent in the label generation. So we have a feedback, either we want it on the tracking level or on the detection level. And thereby you can improve many parameters. For example, you have association thresholds. You can choose a better clustering method. You can learn a motion model, or if you're working with a multiple motion model, you can learn the transition matrices. Everything can be derived from our system. And furthermore, it should be possible to include more sensor data from different sensors. This improves the whole system at the beginning, because you have a more precise tracking, you have a better shape estimation, and I'm sure you get better kinematic estimations. And you can provide the labels for all sensors. That means maybe you want the object and information for LiDAR data in a box, which is easy to calculate when you have the full object information, but you can also derive the association information for radar data. And again, you can, with the automated feedback, you can improve your tracking system. And this doesn't hold whatever. If you want to have a high-level fusion approach, you can improve sensor-based tracking. You can improve the parameters for fusing the tracks on a track level, but also the association, the track-to-track association is then evaluated. And you have a statistical analysis of your tracking system with the labeled data. So to come to the conclusion, I wanted to introduce BAAS with this talk that allows to automate the annotation task as far as possible, and to reduce the effort of labeling measurement data. But what is also important is that we have the architecture for an ongoing parameter optimization in our fusion system. And this allows us to evaluate our whole tracking system and to improve it step by step. So far, we have not replaced manual label work completely, but in the future, I think that might be as well possible if you use unsupervised learning approach. Yes, this was my talk so far. Thank you very much.
Thank you, Stefan. I think we have time for one question, maybe. Does anybody have a question? Don't see anything. Maybe I can ask a question. So what do you think are the right, I mean, here you explored basically radar with, what do you think are the right combination of modalities for detection in general? Or what are your thoughts on that?
You mean which sensor setup?
Yeah.
For detection?
Mm-hmm.
Yeah,
and tracking, basically.
I think I would clearly stick with radar, LiDAR, and cameras, because yeah, every sensor has its benefits. You can use the radar for fast object detection, and you have the direct velocity measurements, but camera can provide us classification information very accurately. And with LiDAR, you have a better shape estimation. You can maybe have a better estimation of orientation. So all three of them will be needed for accurate detection and tracking.
Okay, thank you. Are there any questions in the audience? Okay, I don't see anything here. Thank you, Stefan. I guess we can move on to the next talk. The next talk would be pre-recorded. So just gonna play it from my side.